So this next set of talks is for the Test of Time Award, and this is going to be a very truly hybrid experience because it's one talk with 3 virtual presenters, and I think 3, although I only see Paul on the screen at the moment. Hi, Paul.
Hello. Hi.
Hi, good to see you. Yeah, so we have 3 virtual presenters and 1 physical presenter. Shang-Hua is here. Do you want to come get mic'd in preparation? I don't know. Do you want him to be mic'd? Because you can turn the mic off, right? Yeah. Cool. So while that is all getting set up, I will present the awards. Okay, great. So this talk is going to be for the SIGecom Test of Time Award. This is the award for the best paper in the last 10 to 25 years, and it's the most prestigious paper award that the SIG offers. This 2022 award was given to 2 papers, actually, so a combination of 2 papers that basically settled the complexity of computing in Nash equilibrium, which has, I think, been a transformational result in the field and has had a lot of impact, not just in computer science, but also in economics, getting economists to question solution concepts from a different perspective than maybe was traditionally considered. And so, you know, it's been a really impactful set of papers. The papers specifically cited by the award committee, which, by the way, was chaired by David Parks, so thank you, David, consist of The Complexity of Computing in Nash Equilibrium by Christos Daskalakis, Paul Goldberg, and Christos Papadimitriou. This appeared in Stock 2006 and then was published in the Siam Journal of Computing in 2009. And then after that, we had Chen, Xiaotie, Deng, and Shang-Hua Teng publish a paper that was titled Settling the Complexity of Computing Two-Player Nash Equilibria, and that appeared in Fox 2006 and was published in JACM in 2009. So many congratulations to the authors. We have, for the person in the room, a physical participant award, so you can get your award. Thank you. For those online, we have more awards. Come and get them. We will, I think, try to mail them to you, but yeah. And with that, I would love to turn the floor over to our first speaker. I forget in which order people are speaking. Yeah.
Hi, everybody. Can you hear me?
Yes.
Hi, Nicole. Yes. Okay. Cool. Can you see these slides? Can you see my screen? Like.
Yes, we can see your screen now. Yes.
Okay. Cool. So first of all, on behalf of my co-authors and I would like to thank the award committee and whoever nominated us for the Test of Time Award. It was very nice to remember our interactions at the time leading to this result. So I guess for the next half hour, we're going to have 35-minute talks, one by Christos, one by Paul, and one by me, followed by a talk by Shang-Hua Teng. So Christos actually couldn't be here because it's so we're both in Greece and it's very late here. So he actually sent me his slides, and he also sent me some text, and I'm gonna pretend to be, although it's very hard to be Christos Papadimitriou, I'm gonna at least I have the text and the slides. So, I'll try to do my best. So okay, so this is Christos' part of the presentation. Okay, so now I'm reading Christos' text, right? Okay, so Kenneth Arrow was one of the kindest people I have met, and probably the smartest. At that time, he had been interested in information in economics, and I believe he was getting into computation. He hired me to the OR department, jointly with computer science, in 1982. He kept handing me draft papers folded on the long dimension to fit his jacket, the jacket's breast pocket, papers by economists who were trying to think about computation. He wanted me to do this better. Deng Xiaotie's thesis was inspired by one of these. My work with Michalis Giannakakis on bounded rationality by another. And Chen started me thinking about Nash equilibria. In 2016, at the age of 95, Kenneth Arrow gave an unforgettable inaugural talk at the Simons Institute semester on economics and computation. We lost him months later. Nimrod Megiddo had already been working in the computation and games interface. He had also thought about Nash. We exchanged ideas and realized that to understand Nash equilibria, we needed to define a new class, TF&P, so total search problems in NP. It was an exotic curiosity for a couple of decades. Now it sits at the center of discourse on P versus NP and cryptography. It contains essentially the only known intermediate problems between P and P complete. I kept thinking about TF&P. It took me 5 years to write the 1994 JCSS paper because new ideas kept coming and the math needed care. To achieve completeness, TF&P problems must be categorized in terms of their proofs of totality. The finitary existential lemma used by each proof. We had already defined PLS with Michalis and David Johnson, based on the principle that every DAG has a sink, which is the lemma in the heart of PLS. PPP was defined independently by Steve Cook, based on the pigeonhole principle. Then PPD and its famous resemblance with my last name. I really had not noticed it until a reviewer complained. If your name is Papadimitriou, you get used to seeing substrings of your name. The lemma for PPD says, every path that starts somewhere must have another end somewhere else. I believe this paper is where it was first conjectured that finding Nash equilibria is a PPD complete problem. For 10 years, I would publicly opine that this is the second most important open question in complexity. But I believe that I was not working on it actively. I was hoping others would. Then 2 young researchers came to my life. With Christos, then a first semester PhD student, we started making ill-fated assaults until we realized that the Nash proof, so proving that Nash equilibria are PPD complete, will not be like a reduction, will not resemble reductions, NP completeness reductions. A reduction from SAT proceeds from left to right. The Nash proof needs to close a full circle. We started looking for full circles. Then Paul visited Berkeley from Liverpool, and he got interested in creating gadgets for simulating, of all things, arithmetic by games. By the summer, the three of us were debugging the proof that you know. So this is Christos, writing from Ikaria. And next, I'll turn it to Paul to give us, some ideas in the heart of the PPD completeness proof. Paul?
Thanks very much, Kostis. Now, if you're displaying the slides, I think I'd need you to move to the next slide. Is that okay?
Yeah, can you see the slides?
I can see them, yes. Great, thank you. So, right, I'm going to say a little bit about how the paper evolved and give a few hints about the proof ideas. So, as we've heard from Kostis, Christos gets the general question from Ken Arrow back in the 80s. And I was recalling that the first time I came across these topics was back in 1991, which at a meeting, a sort of summer school, which was the 20th anniversary of NP completeness. And it attracted a bunch of students, including myself, along with various luminaries of the complexity theoretic world. Mihalis gave a talk called The Complexity of Local Search, which introduced the concept of PLS. And Christos's talk, Complexity as a Scientific Metaphor, it touched on the game theory. I do not, my notes do not mention PPAD explicitly, but it was somehow implicitly, I think, there. So I feel that I got quite an early introduction to these ideas, but then I went back home and got back to my thesis, which was about other completely different material. Anyway, back in 2001, I started to take an interest in game theory, and one little factoid that struck me was the point that every game has an odd number of Nash equilibria, at least if it's a non-degenerate game. And that's a kind of interesting point when you think about it. So why is that? Anyway, I went to see Christos until 2005 on a sabbatical, and Christos told me to read his famous paper on the complexity of the parity argument and other inefficient proofs of existence. It was maybe less famous then than it is now, but anyway, that was fun. And yeah, could you move to the next slide, Kostis? And yes, so the end of line problem, which is the kind of key to the complexity class PPAD. As Kostis was saying in his part, the idea is that we have a directed graph, and we assume that if every vertex has got in degree and out degree at most one, then we've got a collection of paths and cycles. And suppose you're shown a particular vertex of the graph, namely the one in red, think of that as being the one in red, then we can, that vertex has got degree 1. We know that somewhere else in the graph there must be other vertices of degree 1. If you take a look at the picture, you'll see 3 other vertices of degree 1 marked by yellow stars. And of course, this is this end of line problem. The graph is presented concisely as, via 2 circuits, where the circuits called successor and predecessor tell you the neighborhood structure of the vertices of the graph. That makes the problem hard, seemingly. And notice that there are an odd number of solutions. This kind of gives away this sort of key point about there being an odd number of solutions, how it relates to Nash equilibrium. The fact that the Nash problem reduces to this, and our challenge was to reduce in the other direction. Okay, Kostis, can you move to the next slide? Great. So yeah, so as Kostis was saying, we had 2 quite separate lines of inquiry. And in fact, while I was visiting Berkeley, I didn't actually meet up with Kostis at the time. He was looking at an approach using a gadget composed of n players in a game that could do Boolean circuit-like things, and trying to figure out how to close the loop, as he put it, which is to say that a game has to be a kind of closed system in which each player is dependent on what the other players are doing, and there's nothing that corresponds with input and output vertices of a Boolean circuit. And the question that I came along with was slightly different. I found out about graphical games from somewhere. Take a look at the picture at the bottom of this slide. A graphical game is a kind of network of players where each player's payoffs can depend on his neighbors. And in fact, this is a bipartite graphical game, which means that the graph is bipartite, indicated by the color coding of the players in the graph in my picture. So graphical games turned out to be nice because they can be made to look like arithmetic circuits. They're kind of structurally circuit-like in some way. And if you give the players the right payoffs, they basically can simulate arithmetic gates. And Christos brought these ideas together along with an averaging maneuver, as we call it in the paper, which allows you to implement a kind of comparator gate, which lets you check which of two quantities is larger than the other and do something reliably if one of them is or else the other one is. So those ideas all came together very nicely. Right, Kostis, can you move to the next slide? Okay, thanks. So we have a sort of sequence of results in which, to begin with, the problem graphical Nash of finding a Nash equilibrium of a graphical game turns out to be equivalent to what we call 4-Nash, 4-player normal form game. And by virtue of the averaging maneuver, we could use the use these games to encode end-of-line circuits as required to get the initial PPAD completeness result. And shortly afterwards, Christos and Kostis, and independently Chen and Xiaotie Deng, managed to push this down to 3-player normal form games. And finally, all during 2005, this was a flurry of improving results. Chen, Deng, and Teng reduce all the way down to 2 players, getting the desired results. Okay, if you can move to the next slide, Kostis. And, oh yes, one proof gadget, which is fun to illustrate in this way, is that one way to think about how to represent graphical games in terms of normal form games is to imagine that the red players and the blue players in this graphical game are kind of represented by a sort of giant players who kind of manipulate the individual players of their color. And essentially a normal form game can in fact simulate a graphical game using that general idea. Okay, next slide, Kostis. And so I think this is my the last slide that I will present, which just for fun, Bernard von Stengel, I think I'd attribute this to him. He thought about PPAD as standing for pretty pictures and diagrams. And here are a couple of these diagrams indicating Sperner's lemma. The one on the left comes from Christos's original stock 1990 paper, and it's a picture of Sperner's lemma. And you can see, I hope, that it shows how there's a kind of directed graph having degree 2 that emerges from the Sperner's lemma diagram. And subsequently, over the years, we have developed more and more sophisticated looking diagrams like the one on the right. But I hope it goes without saying that the one on the left is much nicer fundamentally. So that concludes my part of the presentation. And I think, Kostis, you will continue by telling us a bit about the further work from our paper or papers. Thanks.
Yeah, thank you. Yeah, thank you very much, Paul. Yeah, so picking up from where Paul left it, so I hope you can see the this new kind of like diagram. So by September, so there's a little bit of a lag on my side. So by September 2005, our proof that Nash equilibrium computation is PPAD complete had coalesced, into an interesting architecture which beautifully combined all three problems anticipated in Christos's 1994 paper. After various obstacles since January 2005, when I started working on the problem, all the pieces were falling in place. We knew at that point we had, by the summer we knew that the end was in sight. So the most intricate components of the proof of this architecture were two. First, reducing a stylized version of Brouwer's fixed-point theorem computation problem to a satisfiability problem for arithmetic circuits that contain cycles. And the second was the implementation of the arithmetic gates of this circuit, such as addition and multiplication via small graphical games that were composed together. So given our original implementation of these arithmetic gates using graphical games, we could ultimately show in the way that Paul illustrated with this, like two master players who are manipulating, players in the graphical game, we could show that four-player Nash equilibrium computation was hard. In November, like a couple months later, Christos and I, independently, Chen and Deng, as Paul described, improved the gadgets to remove one player, so to show three-player Nash is hard. And ultimately, Chen and Xiaotie observed that we had been a bit silly, both, Christos and Paul, and also Xi and Xiaotie in like the three-player Nash. We had been a bit silly in trying to implement general multiplication gadgets because only multiplication by constant gadgets were actually used in the proof. And this, which ultimately enabled them to, basically completely solve the problem and show that two-player Nash is hard. So in the past 10 years or so, our understanding of equilibrium complexity in particular, and TF&P in general, has exploded due to the work of many amazing researchers beyond what, us three could have imagined at the time. The community has really fleshed out the complexity of approximate Nash equilibrium computation. And incidentally, this is a question that John Nash himself asked me about after I gave a Carlyle Prize for this work at the Games 2008 Symposium Congress. We also by now have both upper and lower bounds for special families of games, such as games of constant rank. Some references are here on the screen, which are surprisingly, they're very close to zero-sum games, but are surprisingly PPD complete, and anonymous games where approximate Nash equilibria can be computed efficiently using tools from probability theory, despite the fact that their exact Nash equilibria are PPD complete. PPD completeness results have also been extended by lots of people to Arrow-Debreu equilibria and Fisher, equilibria in markets where goods are complements. And finally, important work by Edesam and Yanakakis defined the class fixed P, which captures the complexity of computing an exact Nash equilibrium and an exact fixed point, which in principle can be in irrational numbers. So that has also been very impactful in this space. An explosion of activity has also took place in the broader, TF&P landscape, where people have fleshed out problems whose complexity is characterized by other classes like PPA, the class of the undirected parity argument, as well as the class PPP, which is the class of the pigeonhole principle. Some important recent developments happened in CLS. This class was defined by Christos and I to capture an important swath of problems lying in the intersection of PPD and PLS, such as Banach fixed point computation and computation of mixed Nash equilibria and potential games, problems for which solutions exist by both a fixed point argument and a potential function argument. Little did we know that the class we defined in 2011, 10 years later, would be shown to actually capture exactly the intersection of PPD and PLS, as was shown by the recent breakthrough result by Fernley, Hollander, Goldberg, and Savani. So, okay, a bunch of things, have been shown hard, okay, so for various classes in TFNP, but is there any other evidence that these classes are hard besides the fact that they contain a lot of interesting problems? On this front, there has been a growing and important line of work providing cryptographic evidence for the hardness of CLS and therefore all the other classes, because CLS is like at the very bottom of the hierarchy of these classes. And these cryptographic hardness results are based on progressively weaker and therefore more believable cryptographic assumptions. We are not there yet. I mean, if you look at, especially for CLS and PPAD, but the progress that has been done on that front is truly impressive, and it connects to cryptography and other parts of complexity theory. Last but not least, TFNP is spreading its wings to influence another field, that of machine learning. After the vast success of deep learning in single-agent learning challenges, it is setting its eyes to multiplayer learning applications. However, in those applications, gradient descent, the main optimization method used in deep learning, has been proven unsuccessful, which poses a very normative problem, right? I mean, and the normative problem is there a general purpose optimization framework for this multi-agent learning setting? Which is sort of like a little bit different from like our interest in Nash equilibrium computation, before. So before, I mean, for many game theories, like our interest in Nash equilibrium was more from like a descriptive point of view, like, kind of like trying to understand whether it makes sense to expect that, games and markets out there are at Nash equilibrium. Over here in machine learning, we're actually trying to design those agents. So like we actually are the creators. We have to endow these agents with, some, ability to do some computations and, like targeting some optimization goal. And over here, gradient descent, like the standard method used, is not good. It has been unsuccessful in this space. So in recent work with Daskalakis and Zabetakis, we show that there is an inherent barrier in multi-agent settings where the utilities are non-concave, and that barrier says that we have to rethink the deep learning foundations in the multi-agent setting, and in particular, TFNP,
Okay, so the COVID really created a challenge that I'm in fact the only person here in the 6 people. So first I would like to congratulate everyone. I saw them virtually now, and I would like to say a few words. For Christos, whether or not we are officially his students, he actually is our mentors. His vision has been guiding us not just in this, but essentially throughout our own career. And you all know Christos, the passion of him about computing, science, or life is just totally contagious. So Paul and Xiaotie and I are from same generation, so we received our PhD about 30 years ago. So it has been wonderful to grow up with them by reading their wonderful works and getting their brilliant insight throughout my career. And because we have many students sitting here, there's a lot of students, I would like to share this, that when Christos and she did this Test of Time Award, They both were students. And, talented, creative, and, have very wonderful taste. And so it's, precious thing in life to watch them to grow and shining continuously, brighter and brighter, to be leaders of the field. And in fact, I remembered when I was walking today to the conference that in the early 2007, when Dave Johnson asked me to be the SODA chair, and finally I sent him the PC list for approval at that time. And David called me and said, what is the status of Chen and Daskalakis? I said, they will defend before the deadline of SODA. So David paused and he said, we usually don't have students and postdocs on the committee. And I said, because we recently included algorithmic game theory during the last few years to SODA, and in this subject and a few other subjects, they both are my teachers. So there's a long pause, and David said, in that case, they are both approved. So thank you to both, and for that was 15 years ago, for being a wonderful friend and brilliant teachers. So I think hopefully this also will provide you, in the spirit of machine learning, a little bit of training data of my accent. So now I can enter a little bit technical discussion with a low. Once we know that the computation of the Nash equilibrium is hard, clearly one of the central questions is how quickly we can approximate them. And in fact, it was known before the PPAD completed result that essentially we can approximate them in quasi-polynomial time, okay? So the question is, can we do faster? And the quasi-polynomial time is just based on sampling. And in fact, there's many notions of approximation, and I'm not going to define them precisely. And they're basically built upon different views of the mathematical view. And some build upon, when you change strategy, how much change. Some build upon a beautiful notion by GPT about the complementary view. That is, if you have enough gap, your opponent will play 0. And there's a numerical view that is, can we get log n bits of the equilibrium? So I guess I lost the cursor. So one of the optimistic questions is, can we get a fully polynomial approximation scheme that is running in polynomial time in n and 1 over epsilon? Or can we get log n bits, usually numerically we call short, in polynomial time, okay? And so those two questions also are intrinsically connected with another question about a classical algorithm. It's called Lemke-Hausen, that is for two-player games. So in some sense, Chen and Deng's result really put also highlight on what is connection to this classical result. And so in fact, when Dan Spielman and I were giving talks on the smooth analysis for simplex algorithm, the most popular question people ask is, what is the smooth complexity of Lemke-Hausen? Because it's very natural, right? Lemke-Hausen is a simplex lag, right? So in fact, there's a deeper connection. If we can solve two-player Nash in smooth polynomial time, then we got strongly fully polynomial approximation. So it's connected in one direction. But it turns out that game and economics in some sense are hard problems. And in this case, it is hard to approximate, even to say 1 over n as epsilon. Okay. So this means there's no f-pitas for two-player Nash. So let me briefly outline this. This will just be a very sketchy proof. That is, following the framework that Paul and Christos outlined. So the whole starting place is Sperner's lemma, or discrete Bravos fixed point. And in the case when Chen and Deng proved the two-player Nash is PPAD hard, so essentially they take a circuit that encoding a large colored grid for the discrete Sperner's lemma, and they encoded them into a two-player game. And one thing they know is that A, these two games are small. They only have polynomial dimensions. And B, if you get accurate enough, namely 2 to the exponentially precise equilibrium, you can come back to get panchromatic simplex. That is a discrete fixed point. Okay? So when you try to get approximation, essentially we need like 1/n precision, or sometimes even lower precision. And this is just like, when I try to read and I drop my reading glass, essentially you don't even see the fixed point anymore, right? So the precision here is all exponential, right? Because we have 2 to the n grid points, so which means you need n bits to encode a grid. But if you only have log n precision, it's basically n precision, which means you're in log n bits. So essentially you don't even see the grid anymore, right? So essentially the outline of proof went through that we went up to high dimension to reduce precision. And we're able to build, for example, in n dimension, 8 by 8 and by 8 fixed point, just like Sperner's lemma extend to high dimension. And we are also, just like lower dimension, search for critically the panchromatic simplex. And one of the key projects actually turned out to be very, wonderful project at the first step. It's an origami project. That is, you need to fold this exponentially big two-dimensional sheet. Somehow you want to topologically fold them into this n-dimensional, very narrow grid, right? So that's essentially the first step, and there's a few other technical steps essentially allow the argument to go to show that there's no FP-TAS for Nash equilibrium. So this really showed the intrinsic difficulty of those problems. And this clearly will also extend to, you cannot compute in log n bits of the equilibrium. And the Lampe-Hausen itself does not have smooth polynomial complexity, because otherwise you can return to approximate them. So the result of the two-player Nash by Chen and Deng, and the approximation result, and many of the early build-up, like Christos talked about, relative economics, really also brought a new insight into exchange market. So for example, the classical exchange market is you have endowment, you have utility, and then Arrow-Debreu proof on the mild condition, there's a sort of market clearing price, and this basically governs the exchange. And when the utility is linear, actually, this all can be solved in polynomial time. Almost like a zero-sum game can be solved in polynomial time. And so in fact, through the two-player Nash and other expanded build-up, essentially one is able to prove almost whenever you have any mild non-linearity, it becomes PPAD hard for the market. So market is intrinsically hard. And so I think Christos already mentioned the equilibrium has been greatly expanded to, many new generation come in, get much sharper result. And the new computational class has been defined, and more application has been extended. And so I would like to close, just give a little bit of high-level concept of what happened in the whole process. So, decades ago, when von Neumann proved the minimax theorem, he also used a fixed point. And of course, that later on was improved by linear programming duality. And when Nash gave his first proof, those proof with the early proof of Nash is very similar in spirit. And so mathematicians like Herb Scarf used to ask, is fixed point necessary for Nash, right? And for a long time, people couldn't find the right language to argue for that. So then through the computational lens, a great man thinking hard, he began to see lines and paths and circles. And really, Christos defined this framework and gave the right language to argue that the fixed point is indeed necessary for, intrinsic for Nash's argument. And so let me end lightly, but through computational lens, you can see many things, right? So for example, 10 years ago, 15 years ago, I have a student in BU, tall, 2 meters tall, funny, and the kind of student, double the advisor's life. And so when he saw the Sperner's lemma, he said, I don't see pass and cycle. But you know what I see? I see a board game. So he designed a board game and say, if you play continuously, someone has to lose if panchromatic triangle show up, right? So then in 2011, one day Herb Scoff called me, and he said, Shang-Hua, can you do me a favor? I'm going to Jerusalem for Arrow's 90th birthday. Can you load this the game that you and your student designed on my laptop? In my talk to Arrow, I want to show him this game. So you can see through the computational lens, economics and computation has many unexpected connections, and I'm sure more and more will be explored and discovered. Thank you.
Thank you. I think in the interest of time, we'll take the questions offline. I just want to thank again and congratulate all the speakers. And I really enjoyed hearing about the history and how the results evolved and who was where and when. So that was really fascinating. Thanks for the great talk.
Thank you.